Hello there, my name's Pippa Connolly. I'm going to talk to you a little bit about my life as an engineer and some of the things I've done. First of all, what woke you up this morning? Was it your body clock? Was it an alarm clock? A more analogue version? Was it your smartphone, or was it something like that? There you are, there's an engineer already. Had an involvement in your daily life. You've got an electronic engineer, electrical engineer, mechanical engineer, process engineer, all of them working away to make that little thing that wakes you up. I'm an associate professor here at Monash, and I'm involved in a number of different things, including a lot of industry engagement work. Basically, my background is civil engineering. I'm currently involved in lecturing some civil engineering. So you've woken up, got out of bed, you haven't fallen through the floor. Guess what? Structural engineer has been making sure that you haven't fallen through the floor. Materials engineers have helped the structural engineer. Walk across the floor, perhaps go to the bathroom, turn the light on. There's the electrical engineers, the power engineers. You might go to the toilet. Wastewater engineers, probably not the most glamorous of engineering, but absolutely one of the most fundamental. Turn the shower on, there's the hydraulic engineers. Had your shower, going to put some clothes on. You think, clothes, what have engineers got to do with that? Production engineering, transport engineering, you've got to get all those clothes to you. Okay, you might have some breakfast, open the fridge. Imagine where you would be without a fridge. So you've got to that point and you're thinking, okay, there are engineers all around. Leave the house, there's even more. Environmental engineers, transport engineers, traffic engineers, public transport engineers. So they're everywhere. Now, you've probably never met any of these people and you don't really know them, but do you really know what they do? So I guess I'm going to try and illustrate that with an example. So first of all, I'll tell you a little bit about the process of engineering. So what an engineer does is, first of all, is going to focus on optimisation and improvement. To do that, you've got to figure out what your problem is. So the first thing you do, ask questions. Lots and lots of questions. So all those little kids go, why, what? Budding engineers. So ask lots of questions, work out what the problem is, and once you've figured out what the problem is, identify the constraints. What are the things that are going to have an impact on how you design something? So work through all the constraints, then you need to make some assumptions. So make some assumptions based on those constraints, all the questions that you've asked. Now you can get to the exciting stuff. Start to explore the possibilities, the what is, how about. Start to think laterally. Create some options, come up with some ideas, and at that point you test the ideas, work out which ones are the good ones, go back to your client or the person who set you the problem and try and figure out which one they're going to like the best. But you don't stop there. They'll give you some input, you go through the whole process again. And so it's always about optimisation, improvement, the whole time, getting better. If you want to keep an engineer busy, give them a problem with no deadline. It'll keep them happy for ages. So how do engineers cater for all the possible effects that can happen? The example I'm going to give to you today is about a project I worked on over 20 years ago, and I've worked on a lot of different projects, all sorts of places, but this is one that really, really stands out. So it's in New Zealand. It's the Museum of New Zealand Te Papa Tongarewa, known as Te Papa for short, or Treasure House. So it's sited right there in Wellington, for those of you who know your New Zealand geography. So the little red dot there, it's at the bottom of North Island, just before you get to South Island, and it's in that bay that you can just see there on the slide. So that's basically looking straight out to the ocean, and that keeps on going pretty much to Antarctica. So what I'm going to talk about today is how we actually got that museum to happen. So first of all, we identified, what the project was. And I was brought into it to work with a team of engineers and other people. One of the myths that is around the place is engineers aren't people. Well, yes, engineers probably aren't that best in a lot of social situations, not all of them, but that's not their forte. However, to get any engineering problem solved, you need to work with people. And they're not the people you work with every day, they're the people from all different areas. So there'll be people from the client, other engineers, there'll be people doing all sorts of different things on your project. You have to work with them to get a solution. back to Te Papa. So we're on site and we're looking at the constraints. Now this site has the most unbelievable constraints you could come across, and this is why it really stands out. First of all, it's in one of the most highly seismic areas in the world, and it's on a major fault line. So the fault line runs just behind the site. On that basis alone, most people wouldn't choose to build there. On top of that, it's right in one of the windiest areas you could possibly find almost anywhere in the world. On top of that, you have reclaimed land. So the land has been made by chucking trucks of dirt on the site and just leaving it there, let it settle over time. So not very strong. And in fact, in an earthquake, liquefaction will happen, which some people might know what that is, but those who don't, an earthquake hits, basically the ground turns to soup. You've got tsunami and seeping. So tsunami, because of the location, if you have a tsunami, an earthquake anywhere in the area, tsunami happens, it'll hit the site face on. And the other thing you get with tsunami is seeping, which is the precursor to a tsunami. The land starts to fall away, just like when you're on the beach and the sand is falling away from your feet before the wave comes in. So basically you've got all of those happening. On top of that, as if you needed any more, there's basically a 3-storey concrete building in the middle of your site that you're not allowed to demolish. So quite a lot of things going on that site, and you're thinking, who on earth figured out that was a good site to buy? Well, it is quite a stunning location. The government decided that they wanted to buy it. They set the budget and the time frame. So then you get the political imperative, the budget imperative, add them all together, big problem. So team of engineers, client, and everybody all together. So how did we overcome all of those constraints? First thing, there's that concrete building, the 3-storey concrete building. Don't know whether you can spot in the slide there, it's sitting on rail bogies. Now the reason for that is good old Kiwi ingenuity. Oh, let's just move the building. 3-storey concrete, that doesn't matter. So what they did is they chopped off the columns, slid some rail bogies underneath it, put down some rail tracks down the site and something went across the road, just moved it. Moved the whole building across the site, and it's now a boutique hotel called the Museum Hotel. A very nice place to stay in Wellington. Next thing, all that pea soup for the ground. What are we going to do with that? So, of course, another solution really you wouldn't generally think about, that's a 25-tonne weight with a red circle in it, heading at very high speed to the ground because it's been dropped from the top of those columns. So what they did was dropped the weight on the site repeatedly, so 25 tonnes, until the ground was fully consolidated and much stronger. So again, not a classic solution. And if, in effect, when every single time that weight hit the ground, there was a mini earthquake. So yes, quite an unusual thing to do, and also you wouldn't have been able to do that right in the city centre, even though you're right on the edge of the city. Next solution, base isolators. So this is probably one of the major ones that differentiates this building. And of course, the other constraint that I didn't mention, 250-year design life. Most projects you would design for 50 years. So this building was designed for a 250-year design life. So that means that every single thing you design, the probability of something going wrong gets higher. So you need to design for heavier loads, for heavier earthquake forces, much higher forces, that sort of thing. Solution to the earthquakes was base isolating the building. Base isolators you can see in the image there with the little red arrows on them. They look fairly innocuous. They're actually a very, very sophisticated bearing. So it's layers of rubber and steel with cores of lead. Now this was designed by a New Zealand engineer, William Robinson, in New Zealand, and using a team of engineers globally working on it to actually get the right composition for those base isolators. So effectively, it completely isolates the movement from the earthquake. So imagine the earthquake's coming and everything's moving around, and moving around quite significantly, and the building's just moving a tiny little bit. And that then protects all the artefacts. So inside this building are the most valuable treasures New Zealand has. So none of them can be damaged. And so that's the way that's achieved. The other thing to consider in terms of design life is how much of your design life do you want to actually cater for? Do you want the building to be completely 100% usable after a significant event like an earthquake? Do you want it to be repairable? Or do you want it to be in a condition that everybody's got out safely, you'll demolish and start again? That makes a big difference to what you design for. So the next solution we're looking at, very aggressive site because you're right on the ocean there, salt-laden air, and very, very corrosive. So most of the time, 50-year design life, you design for things to last for that long. 250 years, completely different thing. So materials engineering was really, really significant in this. And we had to do a lot of research into concrete. Now, those panels you can see on the outside of the building, each individual panel is a piece of concrete. And there were lots of different colours of concrete. The concrete's either polished or just left as it is. No reinforcement, again, unusual. So the panels had to be designed the largest size they could be without putting any reinforcement in, because the reinforcement was a risk of splitting the panel apart when it corrodes. The actual design of the concrete mix was one of the things that I was very heavily involved in. So it was like doing a very fancy recipe. And we had to test it. We didn't get the joy of actually testing it like a cake mix. So we just had to keep testing it. So lots and lots of testing on the concrete until we got it right. That was certainly a very iterative process. The other thing that you can see off to the side there is the bracket that is holding up those panels. Each one of those panels has 4 of those brackets, and they're made of grade 316 stainless steel. Grade 316 stainless steel is the highest grade of stainless steel you can get. Very expensive, very durable. About the only thing that can cater with that salt-laden environment. So here it is on site. Now, I haven't mentioned how we dealt with the seaching and the tsunami. So seaching and tsunami we dealt with by putting all the valuable artefacts on the first floor of the building. So designing all the things that were effectively expendable or could be moved on the ground floor. Because the thing about tsunami is you get a warning. Anybody who lives in New Zealand will know that when you're at school, you get taught how to react when you have a tsunami warning. You have time. Basically, that was designed that if there were people on the ground floor, you would take them either out of the building to higher ground or you'd go up onto the first floor, and then everything in the ground floor you would assume would be inundated. So you've got things like the car park and the cafe, childcare centre, which is potentially a bit controversial, but yes, they'd be the first people you'd be moving. So that's how the building dealt with that. Again, a little bit lateral. Another significant benefit is probably the primary factor to design for is safety. Engineers get things wrong, you kill people. You do not want to kill anybody. And particularly if you're looking at structural engineering, the building falls down, there's a good chance you're going to kill people. So one of the major things that this project delivers is safety. If you live in Wellington and if you know that there's major aftershocks happening, the safest place to be in Wellington is in that building, because it's been designed for probably some of the highest loads that any of the buildings in the whole of New Zealand, but certainly in Wellington, have been designed for. So this is the building finished. You can see it's got lots of different shapes, fairly architecturally diverse. There's a lot more I could talk about, but I could go on forever. So I guess what I really wanted to illustrate is engineering is about problem solving. It's about solving a problem, using the information you've got, coming up with a solution to meet all those criteria. So if you know people that you come across, and particularly younger people looking at what they might study, where they might go, just say to them, you're interested in problem solving, capability in maths, science, something like that. Have you thought about engineering? If you've got somebody who's always asked that question, why, how does it work, how's it put together, think about engineering. All I can say now is thank you very much for your time.